Our next talk is Nick Webb from the Jornada Experimental Range. We'll be talking about the integration of AIM data into the National Wind Erosion Network. All right, thank you, Nick.
Thank you. Thanks, Sarah. So today I want to talk about a fairly broad collaborative effort that the Jornada is leading to enhance wind erosion monitoring and assessment capabilities across the US nationally. But a big focus of our work is developing that capability in rangelands, and we're doing this through a national wind erosion research network. All the work that I'm describing is a very big collaborative effort, so I'd like to acknowledge my colleagues at the Jornada and all our network partners that are really making this happen. So I wanted to start by introducing you to what the network is and what it's about, and then I'll finish up by touching fairly briefly on a couple of models and applications that we're developing to support national wind erosion assessments. And one of those is specifically using AIM data. So sort of despite the large number of reasons why we're interested in wind erosion and dust emission, from its effects on rangeland health to air quality and human health, we only have a fairly general understanding of which landscapes are actually eroding and producing dust and what their trends are over time. So analyses of remote sensing data, for example, the Modus Deep Blue aerosol product, has allowed us to identify sort of persistent dust source areas at sort of a regional scale. And analyses of air quality monitoring data have enabled us to look at what the trends are in fine dust concentrations that might impact human health and visibility, and how they're responding to sort of regional climate variability. But we still have a pretty poor understanding of exactly which landscapes are eroding, by how much and when. We don't really know how climate variability is influencing spatial and temporal patterns of wind erosion at the landscape scale. We don't know how land use, land management, and land cover change are interacting with these processes. And we don't really know how climate change might impact wind erosion. Is it going to increase or is it going to decrease? And if we're going to address these types of questions, we kind of need to take a step back and look more generally at how we can enhance our wind erosion monitoring assessment capabilities more generally, and how we can do this in a way that will specifically support management. And in order to do this, we need to overcome some pretty big challenges. And I'm going to talk fairly briefly about 4 of these. The first of them is that most wind erosion monitoring and research programs haven't used standardized methods, and this has really restricted our ability to upscale or generalize our understanding of what's going on across different landscapes, different ecological sites, and under different management systems. Very much connected to this is that most field research and monitoring programs for wind erosion have tended to use sampling designs that have lacked statistical rigor. So having a really small sampling size is just inadequate for measuring a process that has very large spatial and temporal variability. Because it's so hard to measure wind erosion processes in the field, we tend to rely on models to make assessments for us. Unfortunately, though, at the moment, we don't have any generalizable model that works well across rangelands and croplands and for different ecological sites that has sufficient accuracy or precision to really inform management. And to make matters even worse, the models that we do have haven't even been tested across different land use and land cover types. So we've got really no idea of what the uncertainty is associated with our model estimates, and it becomes very difficult to incorporate model information into management decisions. So sort of on the positive side, we do have a number of existing monitoring capabilities that provide us with a really good foundation for improving our wind erosion monitoring and assessment. Both the AIM and NRI programs use standardized methods to collect information about surface soil texture, vegetation foliar cover, the canopy height and the canopy gap size distribution. And these indicators can be combined to estimate the in situ erodibility of landscapes and to estimate actual erosion rates. We also have a number of fairly long-standing air quality monitoring networks, like the Improved Network and the Aerosol Robotic Network, which have a large number of sites across the US measuring fine dust concentrations. And these networks were set up specifically to address issues relating dust to air quality. They've been used extensively in sort of regional dust model testing, but unfortunately they provide no connection with where the dust has come from and what are the management and sort of land cover conditions in eroding areas. And despite their sort of the broad limitations of models, they actually provide us with a lot of potential to integrate information from these different rangeland and air quality monitoring programs, and to include additional sources of information about the land surface, like the vegetation cover and structure, to quantify wind erosion rates and their sort of spatial and temporal patterns. So we saw a big opportunity in this to establish a national wind erosion research network that would focus on integrating the capabilities of these existing monitoring programs, along with conducting some basic research to improve our modelling abilities. So we've set up a multi-partner national wind erosion research network, and we have three fairly broad objectives for the network. The first of these is to support basic research underpinning our understanding of the wind erosion processes and how they're responding to management across different land use and land management systems. Our second objective is to improve the availability of decision support tools, particularly in the form of models and analyses that can support managers and agencies. And our third objective in achieving the first two is really to facilitate collaboration amongst the agencies who are interested in managing wind erosion and researchers, and I guess more on the university side of things, to increase the impact of our work for management planning and policy. And we're being fairly ambitious in this. We want to make it a fairly large and geographically diverse network using standardised methods with an intensive and robust sampling design, and we're making the data open access so that we can really facilitate that collaboration. So as I mentioned, this is a multi-partner network. It involves the USDA's ARS and NRCS, the BLM, Department of Defence, the USGS and the Nature Conservancy. And about half of our network sites are part of the USDA's long-term agro-ecosystem research network. So we really want this to be a long-term effort. I think we have about 16 sites that are engaged in the network, and I've got them sort of shown as stars on the map at the moment. These cover private and public lands and a mix of rangelands and croplands. Got a couple of photos here from sites on BLM land in the San Luis Valley and near Canyonlands. The sites that I have sort of circled in blue, we're planning on installing over the next sort of 12 to 18 months. So at the moment, we have 10 sites that are fully instrumented, collecting data. And we've selected sites that sort of capture the range of land use and land management systems and soils and vegetation communities that we know are susceptible to wind erosion now or may become susceptible to erosion in the future. We really want the data that we collect at these sites to challenge our understanding of the processes and sort of allow us to make big leaps forward in our ability to model them to support assessments. So underpinning our network is a standard methods protocol, and we wrote this to define what instrumentation we have at the sites, our sampling design and how we go about collecting data and how frequently we collect those data, and how we store and manage the data. And we saw this standardisation being very important to address those big challenges for wind erosion monitoring assessment, to enable us to make these cross-site evaluations of what's going on at different scales. So the meteorological and sediment transport data we're collecting is generally consistent with World Met Office standards and otherwise follows conventions that have been adopted by the Aeolian research community. And the standard vegetation and soils methods that we've selected really follow the monitoring manual. And we're collecting and storing data at the moment in DEMA. This means that any data that we collect as part of our network, any analyses that we run and the models that we develop to work on those data can be directly applicable back to the AIM and NRI databases. So this is sort of what one of our network sites looks like. It's just a schematic of how we have the instruments set out. Each of the sites is a hectare, and we're using a stratified random sampling design to get a really good handle on the total sediment transport across each of the sites. So we have 27 sediment sampler masks, which are labelled as those M's in the photograph in the bottom left there, that measure the sort of the horizontal transport of sediment across a site. We have 3 dust deposition traps that allow us to measure what's sort of blowing into the site from upwind. And we're in the process of installing some active aerosol samplers that measure the really fine dust concentrations that will enable us to link the wind erosion processes on our network sites to more regional air quality issues. We're collecting our vegetation data along 3 100-metre transects that we're sampling 4 times a year. We're measuring the foliar cover of the vegetation, canopy gap size distribution, and canopy height. And these last 2 indicators are really important for establishing wind erosion rates. We've heard a lot about foliar cover, but these other indicators are very important too. We're also collecting a lot more information about the soil surface properties, like the presence of physical and biological soil crusts and how much loose sediment is sitting on the surface that could be picked up by the wind. And at the centre of the sites, we have a 10-metre meteorological tower that we measure wind speed profiles and temperature profiles and that kind of thing that allows us to examine the meteorological conditions that are driving the wind erosion processes. We also have fairly good management records at the site so that we can relate what's going on sort of in terms of the physical erosion processes with the site condition and management. So sort of to finish up, I wanted to touch on a couple of models and applications that we're developing to support national wind erosion assessments. And the first of these we've called the Aeolian Erosion Model, or AERO. And this is a numerical wind erosion model that we've developed specifically to operate using AIM and NRI data. And the second model is a regional dust model that we've developed to use remote sensing inputs to provide sort of spatial and temporal estimates of wind erosion at a much higher temporal frequency than we can achieve using AIM and NRI data. And together, the idea is that we'll be able to use both of these models to address those fairly basic but important questions about which landscapes are eroding, by how much and when, how do or how might different management activities impact wind erosion rates and rangeland health, how might air quality be impacted by rangeland condition and management as it influences wind erosion rates, and how might future policy changes or climate change influence these processes. So the AERO model that we developed can suck data straight from DEMA or Teradat in, and on a plot basis query additional information about soil properties like the particle size characteristics of the soil and the atmospheric conditions like the probability of erosive winds. And it can then provide the user with estimates of horizontal sediment mass fluxes and dust mass fluxes. So the horizontal sediment flux tells us something about the local erosion and redistribution at a site. And the dust flux tells us something about the fine dust that's emitted from the landscape that impacts air quality and a range of other processes. So sort of as an example application, we ran the AERO model over just over 3,100 AIM plots. And I've got a summary here on the top of the horizontal sediment flux and the dust flux on the bottom. And these graphs show sort of the probability density of the sediment fluxes for each of the AIM plots. And we've summarised these data at the state, field office and project levels. And we've learned some interesting things about this kind of application. The first thing is that looking at the project level, it's apparent that when we're applying models to integrate AIM data to produce assessments of something like wind erosion, it's really important to consider the sampling design and the implication of that for what your estimates might be. In this case, we know that the Las Cruces District Office used a targeted sampling design. Most of their AIM plots were on a monument with ecological sites and slopes that really weren't susceptible to wind erosion. We know from experience that, in fact, erosion rates are typically much larger in the Las Cruces area than in the Taos area. So that's something that we need to take into account. So looking at the project level, we can use these models to assess the potential effects of different treatments on erosion rates, dust emission and air quality. And in this case, the treatments were different sagebrush removal treatments. The model indicates that removing the vegetation, as you might expect, potentially increased erosion rates and dust emission. And this is something that we observed in the field with degraded air quality as a result of some of these treatments. What we didn't capture in the model was that sometime after the treatments, it rained at the sites, physical crusts formed on the soils, and that effectively shut down the potential for wind erosion. This physical crusting process isn't something that we're capturing in the models. So we need to consider when we're integrating different AIM indicators, what processes can we realistically represent with them and what can we not, and how do we interpret the sort of the model outputs on that basis. So sort of just to touch on our regional dust model, it's really difficult to estimate vegetation structure, for example, the canopy gap size distribution and canopy height, as it influences wind erosion at broad spatial scales. So to overcome this, we developed an approach to estimating different aerodynamic properties of the land surface using MODIS albedo data. And this has enabled us to provide a consistent sort of representation of the surface erodibility and the wind erosivity at a 500-metre spatial resolution, updating every 8 days. So it allows us to look at processes at a much higher frequency than we can achieve with the AIM and NRI data. At the moment, we're implementing this dust model in the Google Earth engine using soil moisture and atmospheric data from the Global Land Data Assimilation System. And the map on the bottom left here shows an example of the output. We've summarised the average March horizontal sediment transport nationally. So with these kinds of products, we can really look at exactly which landscapes are eroding, by how much and when. We can also relate the patterns of wind erosion and dust emission from these models to trends in air quality and the fine dust concentrations that we're measuring with different sort of aerosol monitoring networks. And we can relate them to other observations, for example, satellite observations of where blowing dust is coming from. So at the moment, we're at the stage of calibrating and testing both of these different models using data from the Wind Erosion Research Network. And our next objective after that is to produce estimates of wind erosion and dust emission at different scales using both the AIM and NRI data. And we have a particular interest in developing applications or case studies at the BLM field office level to help us start to interpret relations between different management activities and wind erosion rates. We'd then really like to sort of link our estimates of wind erosion at the landscape level with regional air quality issues and use AIM and NRI data to help us interpret these regional dust model patterns to look at really what's going on at the landscape. And overall, we see that sort of by combining these modelling approaches with the existing data from AIM and NRI and these air quality monitoring networks and our own observations through the Wind Erosion Network, we should really be able to enhance our monitoring and assessment capabilities. Thank you.
Great. Any questions for Nick?
Great stuff, Nick. So the first question was about the validation and information models. The second question was about the soil that you're using and what would be the optimal soil inputs that you would have, and if those two coincide.
Yeah, they don't coincide. So at the moment, we represent the erodibility of soils based on the particle size distribution. So not the texture, but a really finely resolved particle size distribution. Because the model that both of these models are sort of force balance models. So they look at the energy of the wind that's being applied to individual particles and how they interact. So to incorporate different soil properties into that, we'd need to look at what, I guess, probability density functions of grain binding energies for different crust types and their distributions over surfaces, and the crust hardness, which sort of affects the rebound energy of grains on the ground and how they can emit particles. So we're so far off that, which is why we've taken this sort of remote sensing approach to estimating just the aerodynamic properties of the surface at the moment.
Would sand fractionation help you out?
It would. So at the moment, what we're doing is we have a fairly basic process that we look at the surface soil texture, for example, from an AIM plot, and we relate that to the particle size distribution of the soil just in a lookup table. The next step from there would be to produce maps of the particle size distributions of soils, and in that case, sand fractionation could help us map those particle size distributions. Yep.
Great. Thank you, Nick.
Okay.